Welcome, my name is Peter Pavlhuber and this is a course on probability theory. To be more exact, it's a course on probability theory which is based on measure theory. So it's not a very basic course where we just throw some dice, but we are going to prove central theorems in probability theory, such as, for example, the law of large numbers or the central limit theorem. In this video, we are starting and we are going to recall some notions from measure theory. For example, sigma algebras, measurable spaces, LP spaces, densities, and similar things, and some inequalities, for example. And you will find the whole course on my homepage, and I will also link it in the description. Okay, let's get started and dive right into it. So we are actually going to start with a typo here, but I think you understand what we mean here. So to start with probability theory, we need a probability space omega fp, and I somewhat assume here that you took a course in measure theory. And that means you know what a sigma algebra F is. That means you know what a measure P is. So it's actually another typo. So this is also the same P as this here. So that's a probability measure, which is a measure with the property that the whole set has measure 1. So that's the very basic thing we need. We need also random variables. They're usually denoted by a capital letter, although they're just maps. So from omega to E, and E very often in this lecture is going to be a metric space. X measurable is called a random variable. It's called real valued if the E here is R. Please also recall what the Borel sigma algebra is, as we have here, which is the sigma algebra which is generated by the topology on E, and the topology in E is given by the metric on E. So basically, a random variable is nothing but a measurable map. Then what else? We need the distribution of a random variable, which you know if you took a course in measure theory under the name of image measure. So this x star p here is the image measure of x under p, and is also called the distribution of x. We say that two randoms are identically distributed. Well, guess if they have the same distribution. And sometimes we then also write x equals y in distribution, thus the D here is for distribution, or by the tilde here. Then let's recall some distributions. And we are going to do this by using this notation here, f dot mu. So that means mu is a measure, f is a function which goes from the state where the measure is going to be defined on, n0, to r plus, and that's a density. And f dot mu is the measure with this property here. This measure evaluated at this set is the sum over all, well, evaluate the density at I for all I in some set A, which I want to compute here. And here I have the special case where mu is the counting measure on n0. So mu of a set is the number of natural numbers in the set. And f is the density, and you know such measures, they are like here, the binomial distribution, the Poisson distribution, and the geometric distribution. So let's briefly recall them. So you know the formula for the binomial distribution It's a bit thick, I guess, or well, maybe it's okay. Let's make it a bit smaller. N choose x choose n, you can say p to the x, 1 minus p to the n minus x, and that's my f of x here. And that's then, by this I already defined the binomial distribution. For the Poisson distribution, I need a parameter lambda, and then the density is like this here, e to the minus lambda, lambda to the power of x divided by x factorial. You see this here sums to 1 because this here are the elements of the exponential series. And last but not least, for the geometric distribution, I also have something 1 minus p to the x. So that's the number of unsuccessful trials times one successful trial, what I have here. So you basically know such distributions. They will not play a central role in this lecture, but we will always have them in the background somewhere. Here, because mu, what we start with is the counting measure, we call these discrete distributions. And this is in contrast to continuous distributions, where everything is the same as on the last slide, but lambda is not the counting measure here, but it's Lebesgue measure, so continuous measure. But the same formula applies here, so integrate f over lambda over the set A. And for example, if you want to define the exponential distribution like this here, you need to have the proper density, which is lambda times e to the minus lambda x. Indicator x is not negative. And again, here the integral over this function here must be 1, and when you compute this, that's essentially the case. Similar for the normal distribution, which you all also know, 1 divided by square 2p sigma square, e to the minus x minus mu square 2 sigma square. And again, you have to compute that the integral here is 1, otherwise that wouldn't work, because otherwise this here would not be a probability measure. Exactly. Like this here. Okay, now we have real valued random variables. They could be Poisson distributed, normal distributed, whatever you like. And then we need something like an expectation. So what's the expectation of such an x? And here's some clash of notation between measure theory and probability theory, because in measure theory you had something like the integral f of x lambda dx, and you didn't really have special notation for this other than this here. I will also use here notation lambda square bracket f for the integral. But here the lambda is a measure, and here this e here didn't really appear yet. It only is there because expectation starts with an e. So what do we mean by this? I mean by this here p x. So here p is the measure and x is the function. So this is integral x. And then I integrate over the image measure like this. So that's the expectation of the random variable x. And when you recall from measure theory, when such integrals exist, so what you usually have to have is that the expectation of the absolute value of x has to be finite, then the integral exists. and we also need it here. As an example, and what's also a theorem, if we have a measure which has a density with respect to some measure lambda, and if G is measurable, then I would like to compute the expectation of G of x. And this is f of x, G of x, lambda dx. So that's a result. So that's a theorem here. Which I'm not going to prove because you probably and hopefully know this from measure theory. And by the way, you also know that from basic probability theory. So for example, if you want to compute the expectation of x, where x has a normal distribution, what you usually do there, you integrate over this function here and multiply this here by x and integrate over this. And that's the same as here. So f is the density, so that's this thing here, and g of x is x. So that's the x here, what we wrote here, and integrate over lambda. So that's how you already computed expectations in your course Basic Probability Theory. Okay, what else? So we know from measure theory that integrals have at least two main properties. They're monotone and they are additive. So monotone, if x is smaller than or equal than y, then the expectation also has the same property. And linearity, okay, that's self-explanatory probably. Then you can always compute the expectation of x by expectation of the positive part of x and the negative part of x and subtracting. But one of them has to be finite because otherwise the right-hand side is not really well defined. Another important thing that we will also need is that if the expectation is finite, the random variable itself is almost surely finite. To prove this, assume the contrary, that it's infinite on a set with measure bigger than 0, and then this set of measure bigger than 0 would lead to the fact that the expectation cannot be finite. It has to be infinite then. Okay, so that's everything. Yeah, well, that's something we know we need from measure theory. And here's another thing that we are going to need, which did not play a big role in measure theory. Because in measure theory, very often you just have one sigma algebra, maybe A or F or something. But in probability theory, we need more than one sigma algebra. In particular, we want to say something like some random variable z is measurable with respect to a sigma algebra, which is generated by x. So what is sigma of x? And x is a random variable, so that's x to the power minus 1 of a prime in the Borel sigma algebra of E, for example, if x is E-valued. That's sigma of x. This here you can show that is a sigma algebra. That was certainly part of your measure theory course. And we would like to understand when this is the case here. Z is sigma of x measurable. And here the lemma says it's the case if and only if we have a phi measurable with phi times x equals z. Yeah, so there are two things we have to show. So from right to left, we have to show that if there exists phi measurable with phi times phi applied to x of something equals z, then z is sigma of x measurable. And I'm not going to show this because that will be one exercise for you, one homework, which is essentially not too hard when you just plug in the definitions. So you need, for example, this here. So that's sigma of x. So how is phi applied to x measurable with respect to this here, if you know that phi is measurable? Okay, the other direction, that's a construction that is used frequently in measure theory. So first, if z is an indicator function, and I know that z is sigma of x measurable, which means so what pre-images does this here have? So there's a pre-image of 1, which is A, and a pre-image of 0, which is the complement of A. So, and that's sigma of x measurable, which means you can write A like this here. A has to be of this form. A is of the form x to the minus 1 of A prime for some A prime measurable in F prime. But then I can write z equals indicator of A, and A is now indicator of x to the power of minus 1 A prime. And I can write this as indicator of A prime applied after x. And as you see here, this here is exactly the form which I need, phi and x evaluated here. So we proved this direction here for indicator functions. Next step would be to prove it in the same way for simple functions, so sums of indicator functions, weighted sums. And then via some convergence result, which you also know from measure theory, to all available z. But I'm not going to do this here. But that brings me to the next keyword, which is convergence results. What does convergence mean? So I have, for example, real valued, or do they have to be real valued? No, they don't have to be real valued, but that's how we are going to apply this. Real, then I can have the set where xn goes to x, or put differently, that's the set of all omega where xn von omega converges to x of omega. So this is here a set, a subset of my whole space omega. And first claim this set here is measurable. Yes. And if P of A is 1, we say that xn converges almost surely to x. And with this kind of convergence, you can also call this pointwise convergence, because here for every point omega it converges, or almost sure convergence, so almost sure pointwise convergence. We have 3 convergence results. And all of 3 will be used very often in this lecture. First is lemma of Fatou, which does not need any prerequisite. So on one hand, you have the expectation of the limit, to be more exact, of the lim inf. And lemma of Fatou tells you that it is bounded from above by the lim inf of the expectation. And there are, of course, cases where really bigger applies here. And then we have monotone and dominated convergence. For monotone convergence, you have a monotonely increasing set of functions. So for all, or for almost all omega, xn von omega increases to x of omega. Then we have the expectation, so the integrals also converge. On the other hand, dominated convergence. You do not need monotone convergence here like this, but you need pointwise convergence. So that should happen almost surely. And you need a dominating function y. So y dominates all of the xn's in absolute value. And if y has finite expectation, then I can conclude that the integrals of xn converge to the integral of x. Okay. Now the last part of this video, I'm going to show you some inequalities which all should be known from the course Basic Probability Theory, but let me recall them. So we have the Markov inequality, the Chebyshev inequality, Minkowski, Hölder, and Jensen's inequality. So all inequalities, let's start with the Markov inequality. I'm going to prove this also. So the probability that x is bigger or equal than x is bounded from above by the expectation divided by x, where the random variable x has to be non-negative. And the key to the proof is that x times the indicator that big X bigger than small x is less or equal than x. And that's, well, I plot x on the y-axis. I place omega on this axis here. And yeah, x has some form. Let's just do it like this here. I don't know. And for example, the x we are dealing with is here, the small x. Then I have capital X on the right hand side. And on the left hand side, I'm interested in, well, x has to be bigger than small x, so that's this part here. And then times small x, so this function is like this here. Then it drops because here x is no longer bigger than small x. It stays here. Then it's above here, like this. So, like so. And then you see that the green curve is always below the black curve, and that's exactly this inequality here. And now, since the integral is monotone, we have that x times the integral over this indicator here, but the integral over the indicator is just the measure of the set. And that's more or equal than e of x. And that's this inequality. And for the second one, I do not need that x is non-negative, but I'm dealing here with the absolute value, which is of course non-negative. And here I could write p of absolute value of x like this. That's the same as to the power of p is bigger or equal than x to the p. And then apply Markov inequality. And then I will have here the expectation of this here, which is written in the numerator here, and divided by x to the p, which is written here. And that's the Chebyshev inequality. For Minkowski and Hölder, let me also recall these. In the current setting, writing them with expectations and not with integrals. Very often you use the Cauchy-Schwarz inequality, which is here. So I have square roots here. I have here an expectation of a product. I have here the expectation of the single ones, x square and y square, but I take the square root here, and that's the Cauchy-Schwarz inequality. And the generalization of this is Hölder's inequality. Here I need p, q, and r such that 1 over p times plus 1 over q equals 1 over r, and then Hölder inequality holds here. So you have to the power of r within the integral, and the rth root of this outside the expectation. The same for p and q here. And if you take p and q equals 2, then I have r must be 1. Then this term here is the left-hand side in the Cauchy-Schwarz inequality. And p equals q equals 2 is written here. Okay. Minkowski inequality we also need. So they were shown once we proved that these LP spaces are really normed spaces for some kind of triangle inequality. Here I need that p is bigger or equal than 1. There are also versions for p smaller than 1, but we will not need them. In this case we have, well, this here I wrote it down for p also smaller than 1, but we will not need this. So let's focus on the first one here. So that's the p norm. The p norm, recall, to the power of p within the integral, to the power of 1 over p outside the integral. So that's the p norm of x plus y is more than the p norm of x plus the p norm of y, which is then, of course, a triangle inequality. And last but not least, the Jensen inequality. Here phi has to be a convex function, for example, the square function or so. So phi is a convex function, and then the expectation of the convex function is bigger or equal than the convex function of e of x. So for example, you have something like expectation of e to the power of x is smaller or equal than e to the expectation of x. That would be an application, because the exponential function is convex. And from this here, we can, for example, conclude that if p is smaller than q, then LQ is contained in LP. So there's a order in the LP spaces. And how do you do this? If you take e of x to the power of q, I can use the function to the power of q divided by p. So q divided by p is smaller than 1. That's smaller than 1. And here I mix things up, I guess. Because if q over p is smaller than 1, then the function which maps x to x q over p. So that's, for example, q equals 1, p equals 2. That's the square root. And that's not convex, but that's concave. So that's a concave function. And okay, so if you have a concave function phi here, all which happens is that the inequality sign changes its direction. Because if phi is concave, you have that minus phi is convex. And I could use this here for minus, but then the sign just changes. Yeah, and then it makes sense, because then I have it like this. And then I can say if this one here is finite, apparently this one is also finite, which means that if, sorry, I did it wrong because I have p smaller or equal to q here, so that's that's bigger than 1. So everything's correct here. Everything was correct. So q is bigger than p, that means q over p is like a power function, which is convex. And then everything is okay here. And then we've shown if this one is finite, this one is finite as well. So LQ contained in LP, but here we need P smaller or equal than Q. Okay, very good. So much for today. And next time we're going to meet and we will deal with moments and characteristic functions. Okay, hope to see you then. Bye.